Okay, so we're covering antiderivatives at this point. And so antiderivatives are, they undo derivatives. You can think of it as kind of an inverse operation. Yes, you can think of it that way. And so imagine that what we've been talking about for a long time, if you take the derivative of position with respect to time, you get velocity. Now, if you take the derivative of velocity with respect to time, you end up with acceleration. Well, antiderivatives or integrals, the name is interchangeable, depending on who you ask. It does the opposite. So if you integrate acceleration, you're going to get velocity. And if you integrate velocity, you're going to get position. And antiderivatives, as going up, actually do insert information into the problem. And so if you integrate acceleration and end up getting velocity, you'll get the, what is the extra information that will be inserted into the problem? The initial velocity. Okay? So if you integrate velocity, you'll get position. And what is the extra information that you're given? Initial position. So we're going to go over indefinite integrals, and every time we do an indefinite integral, you're going to get a plus c. Well, that's not just an arbitrary constant. If you get into definite integrals, which we'll do after those tests, that plus c actually carries information into the problem. Okay? So let's go over the first rule. And so these tapes are just going to be the basics, the basic rules. Okay? So the power rule. What do we have if we have the integral of x to the n with respect to x? Okay? So if we integrate x to the n, what happens is that it's going to go up by 1 and divide by that number. So this is going to be x to the n plus 1 divided by n plus 1 plus c. But there's an important condition that has to be observed whenever you're doing this, that n does not equal -1. Okay? When n equals -1, we'll get to it in a minute, but that's the oddball out. Okay? But for other things, yeah, it's pretty straightforward. So let's say we were integrating x squared with respect to x. Okay. Well, that just becomes, well, x cubed divided by 3 plus c. So it just went up by 1, divided by that number, and then we had an arbitrary constant. And so whenever you get an antiderivative like this, how do you check your answer that you actually have the correct answer? If you differentiate this, you have to have that. Okay? So let's just, for this one, let's go ahead and show that. So the derivative with respect to x of x cubed divided by 3, now plus a constant. Well, the derivative of a constant is just 0. If I take the derivative of x cubed, that becomes 3x squared divided by 3, which just equals x squared. Okay. So the way you check your work, if you actually do have the correct antiderivative, well, take its derivative and you should get back to where you start. Okay? So we can do a bunch of these. Let's say we did the integral of, why not, x cubed with respect to x. That would just be x to the 4th divided by 4, and then plus a constant. Straightforward. So if we did the integral of x to the 4th with respect to x. So we x to the 5th divided by 5, just plus a constant. Just go up by 1 and divide by that number. So we'll do a couple more examples. Okay, so what if it was x to the 9th with respect to x? That would just be x to the 10 divided by 10 plus a constant. Just go up by 1 and divide by that number, and then add an arbitrary constant to it. Okay, so integers, pretty straightforward. Okay, let's say, why don't we mix it up a little bit? Say the integral of the square root of x. Okay, now the square root of x is really x to the 1/2 power. Okay? So just think, well, what's 1/2 plus 1? That's 3/2. So this would be x to the 3 over 2 divided by 3 over 2 plus c. Just calm this off. Ignore that. Okay, so yeah, so it works with fractional powers as well. And so let's say we were going to integrate, let's say x to the, I don't know, let's say 1 divided by 5. Okay, so we have to think of this as the integral of x to the 1 divided by 5. So what is it going to do? It's going to go up to 1 divided by 5 plus 1. So we're talking about 1 over 5 plus 5 over 5, which would be 6 over 5. Yeah, so it works with fractions as well. Can it work with even something more abstract? Let's say an integral of x to the pi. I mean, that seems kind of weird. But pi is just a number. So what does it become? X to the pi plus 1 divided by pi plus 1 plus c. Is it? Okay? So x to any power. But it can go even further than that. Let's say, what about negative powers? Okay? Well, okay. Actually, starting page. Okay, so I said this works as long as n does not equal -1. Okay? So what is n in this case? N is -2. Okay? So we have to think, we're at -2. I'm going to go up by one number and divide by that number. Okay, so if I'm sitting at -2, if I go up by 1, I'm actually going to be at -1. So this would be x to the -1 divided by -1 just plus c. Okay. All right. Well, if I said, you know what? I want to integrate 1 divided by x to the 7. So you're going to think of this as x to the -7 power. So if you're sitting at -7, remember 0 is way up here, -7 is down here. And so if you integrate x to the -7, if you go up by one number and divide by that number, what is that number going to be? That number is going to be -6. All right. And so let's say we integrated 1 divided by x to the 100 with respect to x. Okay, so think about this guy as you're sitting at -100. 0 is way up there, okay? So we're at -100. If I go up by one number, I'm going to be at -99, okay? So that's x to the -99 divided by -99 plus c. Okay. Well, let's say we have negative fractions. Say the integral of 1 divided by the square root of x. Okay? This is still not n equals -1. And so you can think of this as x to the -1/2 power. So if we're sitting at -1/2, think about what's -1/2 plus 1? Well, it would be +1/2. And so that becomes x to the 1/2 divided by 1/2 plus c. Let's say we had the integral of 1 divided by the cubed root of x. Okay, so you think of this problem as being to the negative 1/3 power. Okay, so you need to think what is negative 1/3 plus 1? Okay, so negative 1/3 plus 3/3. That's really 2/3. And so that would be x to the 2 divided by 3 divided by 2 divided by 3 plus c. Okay, so this power rule works very well. Except now. Okay, so if we consider the case where it's negative 1, so the integral of 1 divided by x. Okay, so I'm sitting at negative 1. If I go up by, all right, so I'm sitting here at negative 1. If I go up by 1, I'm going to 0. And so that would be x to the 0 divided by 0. That didn't make any sense. But let's think, is there a function that if I take its derivative, it becomes 1/x? So do we have a derivative that forces things down to the bottom of the fraction? Well, yes we do. And so this is the oddball case out between infinitely many numbers, and what does this guy come out to be? The natural log of x plus c. And I've seen over the years many students who they see these fractional powers and they try to write them as natural log. No. The only time that this thing, if you have a fraction that's unequal to natural log, is if it's just 1/x or x to the negative 1 power.